Let's talk a little bit about opaque and transparent. I have a material here, plexiglass. What do you think? Is it transparent or opaque? Transparent, because we can see through it. I can see you, you can see me. We can see through it. Well, we can see through it with visible light, right? Because that's what our eyes can see. But let's see if the infrared makes it through there. So I'm going to put this plexiglass between the heating element and the camera. Okay. So is it transparent or opaque? It's opaque for infrared light. Now I have some other material here. This is just a plastic garbage bag. I brought it from home. Is it transparent or opaque? It's opaque in the visible, right? Our eyes can't see through it. Let's see about the infrared. Are you ready? So it's transparent in the infrared, right? That goes through it. So it's interesting to see that the light can be different parts of the spectrum. Materials can be opaque or transparent in different parts of the spectrum differently. Now I'm going to unplug this, let it cool down. And while we have the camera out, I'm going to step in front of it. And you're going to take a look at me in the infrared part of the spectrum. Okay. So my eyebrows are a little cooler than the rest of my face. I'm going to raise them up and lower them. And my glasses, the infrared light's not getting through them, so they look cool. But if I lift them up, then you can see that my face is quite warm, right? Now it's good. Now the interesting thing about my glasses is, right, that they are opaque in the infrared. They're not letting the infrared light through, but luckily they let the visible light through, or they wouldn't be very good glasses, would they? So, transparent, opaque, and different parts of the spectrum. Now, let's take a look at the electromagnetic spectrum one more time, right? We talked about all these different things, radio waves, microwaves. What happens is everything tries to give off energy in the form of an electromagnetic wave. Everything. And so if you have a really, really cold object, it gives off really, really low energy waves. It gives off maybe radio waves. And as you warm up the object, it starts to give off more energetic waves, maybe microwaves. And as you warm it up even more, it starts to glow in the infrared part of the spectrum, like you and I, we glow in the infrared part of the spectrum. And like our little heater here, when we warm it up a little bit more, it starts to give off visible light. And what's the lowest energy visible light? Red. So it starts to glow red hot. And then we warm it up a little bit more and it gives off all the colors of light. And all the colors of light make white. So it starts to glow white hot. So white hot is hotter than red hot. And if we could warm it up more, it would start to look blue. And then it would give off ultraviolet and then X-rays. And if you look at the stars at night, I'm not sure about tonight, but I think it's pretty clear today. Maybe tonight. I think a storm might be moving in. But on a nice clear night, go out and look at the stars. Some of them look white. They're about the same temperature as our stars. The sun, they give off about the same color as our star. But some of them look kind of red because they are cooler than our star. They give off more red light. And some look kind of blue because they're hotter than the sun and they give off more blue light. Now Kimmy's going to tell us a little bit more about light and the colors of the rainbow.
Alrighty, so I have something here that I think most of the adults should recognize and most of the kids probably don't. This is a good old-fashioned overhead projector. So if you don't know how this works, it shines a light from down here up into a mirror. It reflects and shines through a lens and projects in whatever direction we're hoping for. So I'm going to, almost forgot to mention the coolest part. We've modified this overhead projector. We put something called a diffraction grating over the lens. So what this does is when we shine light into it, it breaks up that light into all the colors in our spectrum. So we're going to see that now when I turn it on. Okay, yes, lots of pretty colors, I know. Now kids, you know these colors, right? Yeah. Can you say them with me? Red. Some of you were a little ahead of the game, but yes, they're all the colors of our rainbow. Okay? Now, that's cool in itself, but Sir Isaac Newton did something a little more inventive with this. He not only took white light and split it up into all the colors of our spectrum, but then he took all of those colors of light, put them back into a prism so that it combined into white light. And that is the experiment we are going to try now. So I will turn that off, and we are going to play one of my favorite games. I believe you all know this one. Red light, green light? Great. Okay. So, when I say red light, I want everyone to repeat after me. Red light. And the people in the booth gave us a red light. All right. And now let's go ahead and green light. And we got a green light. And we have something kind of interesting here. So first, we put red on. Then we added some green. And here in the middle, where they overlap, we see yellow. Now, when I first saw this, I was pretty shocked because I've been to kindergarten. And in kindergarten, we learned about primary colors. Red, yellow, blue. And we learned that you can mix all those colors to make all the other colors of the rainbow in different ways. And mixing red and green didn't make yellow when I tried that with crayons. But we have a different set of primary colors for light. So now we're going to add another color to our stoplight here. We're going to go with a blue light. Okay. So red, green, and blue are primary colors for light. And then we have our secondary colors for light, which would be yellow, where our red and green mix. We have this color we call cyan, where green and blue mix. And down here we have magenta, where the red and the blue mix. And the coolest part of all is in the very center, where all the colors mix, we have white. So, now I'm going to go ahead and ask the people in the booth to turn off the green light and turn off the blue light. And we'll leave red, and we are going to talk more about how we actually see color. Can you tell me what color you see here? Good, all right. But we also have to know what color light we're shining on it first, right? So yes. So can we get the white light on? All right, so this is actually a white surface. Now, why is it that just a few moments ago most of us agreed this was red, and now we say it's white? Well, all objects and surfaces absorb and reflect different colors of the spectrum. So this is a white surface, which is capable of reflecting all colors. So when we shine white light onto it, it reflects all colors, and they combine back into white light, and then you see white. This stage is black, and so when we shine white light onto it, it actually absorbs all colors. So we see nothing, which appears black. Now, can we go ahead and get the red light back on? All right. Can you tell me what color you see here now? Red, all right. Can we get the white light back on? Hey, wow, a little surprise there. So on this side, we have red. On this side, we have white. Now, They looked the same in the red light because, as we discussed, white surfaces can reflect all colors. So shining red light onto it, it just reflects that red light. A red surface, however, reflects only red light. So when we shine white light or red light onto it, it absorbs every other color but red, which is reflected back into your eyes, so you see red. Now, next time you see an object that you think is a specific color, try to think about what colors are being absorbed and what are being reflected.
We've been talking about light, we've been talking about color, we've got to talk about why the sky is blue, right? The sky is blue because it's made up of lots of tiny particles. The atmosphere around the Earth is made up of lots of tiny particles. And one thing I didn't mention earlier about refraction, one of the interesting things about refraction is that when light hits it, it takes that different direction, right? It bends, takes a different direction, the angle changes. Well, blue light bends more than red light, and that's how we can put white light into a prism and get the different colors of the rainbow out the other side. Well, the same thing is true when light is scattered by small particles. When light is scattered by big particles, it's all scattered about the same. So when you look at a cloud is made up mostly of big particles. It scatters all colors of light about the same, so all the colors of light come back to your eye, and you see white. Most clouds look white. But small particles scatter blue light more than red. So if I was shining a light from the right side of the stage across to the left, and I had some small particles here, the light would hit that, and the blue light would get scattered toward you and me. And what would make it through? The red light would make it through to the other side. And that's what happens when we look up at the sky. The light hits the particles, blue light gets scattered out. So when we look at all this at the side, we see blue. But what can make it through all the way through the sun, all those particles when the sun is setting? Red light. So sunsets look red and orange, and the sky looks blue. Let's see if we can demonstrate that for you. So we've got some water here. That's going to be our atmosphere. And we're going to put a light on. The light shines through there. That'll be our sun. Now, the camera can only look in one place at a time. So the camera is looking at our side here of our atmosphere. So this is hopefully going to start to look a little blue. And I put a screen here that's showing what the light that comes through. So this is like the sunset. Hopefully this will start to look red on the screen. Now we need some particles in here. And I'm going to use Mop and Glow. Works as well as anything, I guess. And so I'm going to put some particles in here, and we'll stir that up. And as we start to get particles in here, you see, you can start to see the path that the light's taking through here. Okay, we'll turn the lights down a little bit. See the path? I'll wiggle the light a little bit. See, now that there are particles in there, we can see that, right? Okay, so I'm going to put some more in there because we need lots of particles in our atmosphere. This is what you call a stirring sunset. So hopefully, this is starting to get a little bit of a blue tint to it, and this is starting to get kind of an orange-red tint to it, and we'll put some more in here. And this really happens. Sometimes there's a volcano erupts someplace in the world and spews out lots of little particles, smoke into the air, and there are very beautiful sunsets all around the world because of it. In fact, this happened, I noticed just in September. I was up in the mountains, and it was really smoky up in the mountains. We had lots of wildfires in California in that time. And on the drive back to the Bay Area, I saw the most vivid, beautiful red sunset I've seen in a long time. So here's, I'm going to put a little bit more in there maybe. But you can see that we're starting to get this reddish tint to our sunset and this blue tint over here. Now we didn't talk about polarization today, but light that is scattered is actually polarized. And I have a polarizing filter here, and if I rotate it 90 degrees, it blocks that light, and if I rotate it back, it lets it through. Okay, and that's how our polarized sunglasses work. They block a lot of that glare that comes from the sky and reflected surfaces. All right, so blue sky, red sunset. Now if we wait just a little bit longer, I think we'll actually see the sunset. So let's do a little summary. We've been talking about light. We know why that sports car looks red, because the paint absorbs all the colors of light except for red and reflects red back to your eye. We know why it gets hot in there. Did we talk about that? Light, we know about transparent and opaque. Light goes through the windshield because it's visible light, goes through the windshield, right? Glass is transparent for visible light. It gets absorbed by the dashboard and the seats of your car. And then they try to give off infrared, but infrared can't get out. It's opaque to infrared and it gets trapped in your car, and your car gets hot on a summer day because of that. We talked about blue skies and red sunsets. We talked about fiber optic cables. One of the greatest engineering feats of modern times, running fiber optic cables under the oceans, around the continents. There's enough fiber optic cable to go around the Earth over 22 times. We talked about visible and opaque. The X-rays go right through this person's muscles and skin, but not through their bones or their pacemaker. Money. How do those machines count money so fast? This is a picture of a $100 bill and a $10 bill in the infrared part of the spectrum. They've got these stripes on the back that you don't notice normally. Well, the machines look at them in the infrared and very quickly can count the money. Your remote control at home sends an infrared signal to your TV set or your stereo to turn it on and off, change the channel. And if something is in the way, it doesn't work.